Yo, what's going on, X? Oh shit, oops. Yo, what's going on, X? How you doing, man? Mm. Chilling, bro, chilling. So, just continuing system design, trying to understand in like the technical terms, and then I can move on to actually doing like mock system design through Excalidraw. I think that's the. How's your portfolio going? One exam is left. Oh, nice, dude. You're almost done. Do you guys get summer break too, or is that different? Let's say measurement. How quickly efficient or quickly task complete. Scalability is the rate which multiple the which can be performed with a certain unit of resource. 2 months of summer break. Oh, nice. Hell yeah, dude. You excited? You have any summer plans? You're gonna work on your portfolio today? Cool, cool. Right on, right on. Hell yeah. Before it's being served, but can also handle. You going to the mountains this summer? Oh, dude, it sounds like fun, man. What mountains? Need flashcards from my flashcards, man. Oh, don't have flashcards, so I guess I can use post-its. Just need to cut the post-its. Yo, what's going on, Milk? Spending summer snoozing. 3 to 4 day trip? Ooh, it sounds funny. That sounds good. Hello, Unk. Fuck, dude. I'm actually an Unk. So sad. Don't forget, I'm actually, um, I'm actually 50 years old, guys. Might as well call me Gramps again. God damn it. This is maps. Every year you go for the trip twice in summer and once in winter. Ooh, sounds fun. Hell yeah, hell yeah. Yeah, this summer I think uh I'm probably just gonna be trying to get a job and um probably gonna end up working. Maybe just have like 1 month off before I start working. It depends. If I get the contract job, I think I need to start right away. If I get the full-time role, I'm probably gonna take a month off. So it'll be like summer break all over again. But what am I gonna do? I guess visit my parents and then chill at home, play games, relax. I'm a homebody now. That's all I do. Maybe go to a couple car meets. Latency and throughput. Latency can be defined as uh, latency can be defined as the bandwidth, like essentially the time it takes for a request an action to be resolved. So like if I send a request, the time it takes for it to be resolved and sent back to the the person who made the request. Throughput can be defined as the amount of requests that a system can process. Mm. Hey Krishna, hello, hello. How you doing? Isn't it crazy? I'm making flashcards for my flashcards. I'm fucking insane, dude. Latency defines time to perform action result. And then we have throughput, which is the number of actions slash results per unit of time. Number actions. Consistency patterns. When I think about consistency patterns, I'm thinking about the CAP theorem, where we either want, um, through modern consistency patterns, we utilize the CAP theorem such that a system must always be persistent because we are then fighting between consistency and availability. So either we want CP or AP. And CP ensures that we follow the acid principle, whereas AP follows the base principle. Recall definition of CAP theorem. So clients have consistent pure data. Yep. A best effort approach is taken. Weak consistency. So fuck. It's memcached. I need another one for memcache. Do I have any childhood or school friends? Um, I have school friends. A lot of my childhood friends and everyone kind of just like went their own way. So I don't really keep in contact with too many people now. But I think that's part of the whole growing up thing, I guess. I mean, people grow up, people change, right? Is primary to burst. Key value store. Let's see. Showing consistency. What's my favorite place to visit? Favorite place to visit, like dream place? I don't know. I guess, well, Japan was cool. That was like one of my dream places. Um, but I've been there and it was awesome. Uh, dream place. Okay, I don't really have like a dream place. I guess if we were to say dream place to live, then that would change things up. Because as of right now, I can't really think of a place I want to visit. Maybe it's because I'm so focused on just making my life stable that dream place to visit doesn't really matter to me. Dream place to live, though? Good question. I heard Oregon's beautiful, and I kind of want to go. Actually, I kind of want to go visit Oregon to see how it's like to live there. Um, I would say also, uh, I guess living in Japan would be cool because it's so damn clean. But I don't really know if I'll fit culture there just because they're kind of uptight. And that's not a bad thing. It's just kind of how they are. Um, very professional, like 24/7. But also I haven't met like the chill crowd in Japan. Actually, yeah, I have. I met my friend's wife, and they both are citizens in Japan now, so they're chill. Do I like mountains? I do like mountains. I would say Um, Sweden, if I could live in Sweden, that'd be cool too. Oh, actually, yeah, I would want to visit Sweden. I think Sweden is a really cool place to visit. Roads are really nice, and the entire like fucking country, state, country to Sweden. So, yeah, it's just beautiful. So, would want to go visit there for sure. Norway is also really beautiful. Kind of want to go visit Norway. Uh, uh, I mean, I guess as far as living, I want to be allowed to have a really loud car. So if Sweden and Norway won't let me have an extremely obnoxious vehicle, probably would not want to live there, but I would want to visit there. Oregon seems to be really uptight with emissions and stuff too, so probably would not want to live there. Just would I want to live where I can have a super loud car and I would be fine. Not Germany. Germany kind of cracks down on loud vehicles, so probably not Germany. Um, I don't have an answer for you. There are some cool ass places, but yeah, I nothing comes to mind initially except for you know yeah I guess I'm not like a big travel person either. I'm very your dream place is Germany. Oh shit, why? Germany is cool, but I'm a car guy, so the main reason I want to go visit Germany is because I want to go visit the Porsche like headquarters there, like the museum. I want to visit the Mercedes museum as well, and BMW. You live in India, so is it super close to Germany? So you kind of want to just like move to Germany because it's like convenient, or is there or the reason is because you live in Germany. But what about oh no, so you live in India. But what about Germany makes you dream of Germany is what I'm saying, right? Like there's always greener pastures anywhere you go, but you know. You live in a mountain area, you want to explore the cities and clarity of road. Can explain the way you want it to. No, you're good, you're good. Yeah, I hear a lot of people who actually live in India want to travel out and experience other parts of the world. My coworker is actually just like that. She wants to experience like everything that the US has to offer. So she's been to a lot of different areas and yeah, I mean, I totally get that. I think because I've traveled a little bit already, I don't really feel the desire to travel as much. But yeah, I mean, it's cool. It's cool. I totally get it. Performance is system. So performance essentially is uh, the system is considered performant if it can manage um, it can perform. I mean, it's considered performant if it can manage a set of actions or responses with it proportional to its existing um, units of it can manage a unit of work with its available um, resources, uh, whereas a system requires or a scalability itself is defined as the uh, the units of work the units being the units of work being processed in relation to both the available resources and quickly it can process said units of increase proportional to the resources added. Yo, what's going on, Chargeable? Doing good, doing good. How about yourself? Latency and throughput. The latency is defined as uh, the time it takes for an action or result to be resolved, and throughput is the I'm always getting this wrong. Throughput is the number of actions per unit of time. Latency. Yeah, okay. So this one is considered good. Availability patterns. It can be availability patterns, basically like the system can either be always available, usually available, or can cap theorem though. This is basically a cap theorem question. So fuck. Fail over is active, passive, or master if we're talking about servers are public facing, the DNS would need to know about. What is active active? Explain active active. Servers are public facing. Servers managing traffic. Is domain name system. Hmm. Do I know about Shah Rukh Khan or Salama Khan? I do not. What is it? Is it also like a place in India? Like a mountain, probably, maybe? I'm just taking a guess. Potential loss of data. They are superstars, famous in the world. You think I know about it? Really? I can check. This is the first time I've heard about them. Don't believe I am very familiar with him. Uh, yeah, I actually don't think I know about Shah Rukh Khan. Notebook. Oh, is this? This is different. Okay, I thought it was the Notebook. Yeah, I actually don't think I'm very familiar uh, with them, actually. Yeah, I'm sorry to say, I actually don't, I don't recognize them. I'm not really familiar with like Indian pop culture or like Indian films, I guess. Um, Virat Kohli, uh, he is a World Cup champion. Oh, I actually don't really follow soccer either, so unfortunately, also not very familiar. Um, yeah, I think I even have a hard time remembering celebrity names in general, but usually I'm pretty good with faces and I just can't put my finger on them, so I'm just gonna go off the bat and say that I don't recognize them. Yeah, I feel like even when it comes to Japanese culture and even Taiwanese cultures, I don't keep up with like the celebrities or anything. Um, I'm usually pretty uh, well, it's kind of like asking, I guess. Like I like movies, but I usually only stick with movies that are released that are, I guess, popular in the US. Like I don't keep up to date with movies outside of the US, but I think that kind of is usually in line with most people. Um, like I guess it's less so US movies, but like companies, right? So, oh yeah, completely. So like I only stick with like uh, uh companies that put out films that I recognize. So like Pixar films, obviously Disney films. Not that I watch them all the time. Uh, obviously, what was it? Fox? Wasn't it Fox or something? It got shut down, but they used to put out a lot of movies. Universal Pictures, Paramount. Uh, so like I'll know their movies because they're really popular companies and stuff. Solve Leak Code 1229. I'm not doing Leak Code right now just because I have a system design interview to prep for, but maybe once I get back into Leak Code. Can I show you my Leak Code profile? Sure. I think you just look up Codemaster Big Brain and you should be able to find it, I guess. What's going on, Freaky Gamer? What I have created is linked in my GitHub below. You feel free to check it out, and ask me questions if you do have any questions about it. But I'm not creating anything right now. I'm just studying system design because I have an interview in about a week. You're doing a lot of data structures and algorithms, but you're pretty bad in development. DSA does not define you as a developer, so if you want to get better at development, you just need to actually do it. Build a project, look at what companies are requesting for, and showcase your talent through that project, right? You can do DSA as much as you want, but it seems like companies are also kind of leaning towards more practical programming in interviews now. So you might have like the world's best lead code skills, but if you can't code up a component and showcase it during an interview, you're probably fucked. Can I give a proper description of what's going on? I'm prepping for system design interviews. So basically, we're talking about how the client interacts with load balancers, which then gets distributed across a couple different servers. And then the servers will go and fetch the data and how to make the system efficient so that users can experience a high performing and reliable system, right? Depending on the premise. Uh, yeah, no worries, man. AI versus development, which one's better for you? Whichever one you prefer more. AI data analytics, completely different fields. One is obviously more analytics heavy and one is more development heavy. So, do you like building like components and engineering how things fit together to create something, or do you want to are you more like stat driven? You want to create stuff. If you want to create things, then um, you're gonna need to you probably want to do development, but you can choose where to focus in development. You can either do web development, mobile development, game development. The list goes on. So um, it's entirely up to you. You just need to figure out what you like, and then kind of just hit the ground running, right? Well, if you like AI and you like statistics, then go with AI, right? You can't say you like development plus AI. AI is more of a analytics driven um, like programming field. It's not so much like developing like you know a product. I mean, it's a product, but you're gonna have to do more research because I don't know too much about the AI field to give you like an accurate um, opinion about AI and stuff. I will tell you though, doing it strictly for the money is fine, but it'll probably lead to burnout a lot quicker than if you had a little bit more intrigue into the field. But yeah, just a word of caution. Yeah, no worries. Consistency patterns. Where's consistency patterns? We have weak consistency, eventual consistency, and strong consistency. Weak consistency basically stands for uh, weak consistency. Basically just means that when we are, a good example of weak consistency is if, for example, we're in the middle of a video call and there's a poor connection which results in some loss of data. The service will resume when the service for the user will resume at a point where the connection is stable again, but the data that was lost does not get shown. So good examples where a weak consistency system is good is just for like um, voice chats, multiplayer games, stuff like that. The way it does this is through memcache, which is applied on each server through the usage of storing data objects in RAM, which is just a lot faster than trying to access the disk for data. The cool thing about this is it also allows for these servers, multiple servers, to essentially store its own cache, but then it's referenced globally across all servers. So it becomes like this one giant cache. We do have eventual consistency, which is essentially the concept that eventually the system will be consistent. What that means is, um, say for example, there is an example of eventual consistency is um, like I guess like a DNS, right? Like when a DNS tries to, when a client connects to a DNS, there is potential for, or let's say, for example, a DNS is trying to serve a website or a client trying to access a website like google.com with poor connection. Well, at a certain point, when the response is ready to be sent and the connection is stable, it will be served the website. So even if there's poor connection, it will eventually show up. Right. That's my explanation, but does that make sense? Oh yeah, that's right. After a while, right, reads will eventually see it. And how is data replicated? It's asynchronous. Things will happen in the background. Okay. We have strong consistency. The best use case for this is like banking, where the goal is that if there's a connection failure, we want to make sure that there is no change in data. And if there is going to be any lag whatsoever, we will only show the data once it's actually been updated. So these things are handled synchronously. RDBMS is a good example as well. It's a relational database system. Yep. Okay, we'll say this is good. Simply search. Yeah. If you can just post your website here, it's a lot better for me because I am studying system design right now. So performance versus scalability. Performance is the measurement. Well, a system is considered performant if the system can handle a single user efficiently. So what we mean by that is essentially the units of work we have is able to process a request in or an action and serve a response or a result in a timely manner. whereas a system can be considered scalable if the performance of the system can allow for can allow for more units of work. Scalability. A system is considered scalable if the performance, which is relative to the units of the performance relevant to a scalable system is considered performant if the units of work can the units of work can reliably add more units of work relative to the units of actions requested on or applied to the system, I guess. Results in increased performance. Okay, so when something scales, we're assuming that it's actually going to increase in performance based on the amount of resources we had. Generally, increasing performance means serving more units of work. We can also handle larger units of data, such as data sets. Do I have any friends who right now are in AI field? Am I a student or am I working anywhere? Well, I can say I'm a lifelong student, pretty much, always learning. Do I have anyone in the do I know anyone in the AI field though? No. But yeah, no. Um, latency versus throughput. Latency can be accurately described as the time it takes to get a particular action or result, whereas throughput is the number of actions or results. Latency is the time it takes to resolve a action or to return a result or to perform an action, whereas throughput is the units of action or results a system can handle. Number of actions per unit of time, dude. The number of actions or results with regards to time. Availability patterns. Availability patterns are basically so there are a couple of different ways we can solve availability issues, where availability issues come from a single point of failure. So in order to resolve this single point of failure, such as maybe a load balancer or potentially the server itself, we need to apply replication. Replication comes in two different forms. Either we can replicate through master-slave replication, or we can replicate through the active-passive paradigms. So with active-active, essentially what we're doing is there are two servers, they're sending heartbeats to one another. And this can also be considered a master-master replication, but basically if one server dies, the other one will sense that there is no more heartbeat being transmitted. Therefore, the other server that's already active, which is, they were originally splitting the load between the two of them, will now take all the load. And we'll wait until it senses that the other server is available. For a active passive, it's the opposite. We have the active server that is assuming the entire load, processing all the requests, and handling all the traffic. Whereas the passive is not doing anything and is waiting until the the active server dies, and then it will take over. So for pure replication processes, we do have master-slave replication. Master-slave replication essentially is just having the master doing all the reads and writes, but then it will actually replicate its data available to all its slaves. Slaves, unfortunately, can only just read, which is actually better. But the problem with this is, well, if we end up replicating too much, obviously if we have too many reads, that's a lot of data replication, which can lead to data loss because not data loss, but let's say users want to read a specific data. Well, with so many replications happening, the data being read may not actually be accurate because replication process is still happening in the background. So another disadvantage for the master-slave replication system is, well, it adds a little bit of complexity because for each potential, let's say the master goes down, then the slave itself, we need to write some logic to promote a slave to master, so that does add a little bit of overhead as far as complexity is concerned. If we're talking about disadvantages for failovers, there could be potentially inaccurate data being transmitted or data loss in general because let's say the master is writing something, but then the master fails before the data can be transmitted to or replicated to the other master, then the other master actually will never have that data. So that is potentially one problem we would run into. As far as some other disadvantages, or some other disadvantages of failovers. Yeah. Okay. What are some other disadvantages of a failover system? I think that's, I mean, obviously there's a bit of complexity with the code because I mean, we have more hardware too. I mean, that applies to the master slave replication, but I think that's pretty much what I got. More hardware. Yeah, I mean, fuck, okay. Potential loss of data, yeah, so this is good. Let's say availability versus consistency. Um, you don't have friends who have interest in computers, so you want to work with a USA student. Can I help you? What do you mean, like, what do you want me to do? What do you need help with? Availability versus consistency. So this is where the cap theorem comes in place. We are applying essentially a system can only ever have two of the three properties. Either it's consistent and available, or we have consistency, availability, and persistence. And a persistent system is something that we actually always want. I think generally this is the modern way of doing things. System should never go down, so either it's either going to be always available with the potential side effect of it being that the data may not always be consistent, or we want a system that is always consistent, in which case it may not always be available. So that's kind of the general rule of things. It really depends, yeah, atomic reads and writes. It's one all or nothing, essentially. Basically, we're saying the data is not available and it hasn't been successfully written, then we will discard it because obviously it's not available, or it wasn't the process wasn't complete, or the process wasn't complete. Responses to a more recent version of data, which might not be the latest. Writes take some time when the partition is resolved. Let's say this is pretty good. what role am I preparing? It's the same role that I had before. It's still it's essentially a full stack role. Originally, I was front end focused. Um, so I was building a lot of web components for internal tooling at my previous company. But yeah, so I'm trying to aim for a full stack role because I do want exposure to the back end. Plus, I do want to eventually take over some DevOps positions as well, just because it pays more and it has a bit more job security. I don't use WhatsApp, unfortunately, and I don't use any other apps like that actually. So I apologize. Um, so performance versus scalability. Performance is the measurement of which this how well a system can resolve a specific action with its existing resources, whereas scalability is essentially the system can be considered scalable if it increases performance when we add more units, of work relative to the resources, we add as well. Um, yeah, performance is considered. Yeah, so I think that's good enough. Okay. So, yes, this is good. Okay. All right, guys, I'm gonna eat lunch. I'll be right back. Yeah, I'll be right back. What's going on, Raj? Oh, I think everyone's gone already. What's my motivation to do every day? Well, if you're still here, job security or just getting a job, getting paid. Just got done with work, 12 a.m. Yeah, dude, it's late as fuck. That's crazy. Right. Consistency patterns. I think I did this one already, right? Yep. Latency is consistency. Performance is performance is essentially the performance is like essentially um, how well it can handle one specific user, whereas scalability is how well a system can handle multiple users. I guess to be more specific, performance is essentially the measurement of systems considered performant if a unit of work can be resolved efficiently with the amount of resources available. Whereas scalability is we can consider that a system is scalable if it's actually going to increase performance when there are more units of work relative to the number of resources we have. So that's pretty much it. DNS is essentially the domain name system in which where we have readable, memorable domain names for users such as google.com, but then it's actually served through an IP address, which is essentially the location at which this domain sits, basically. DNS, it's hierarchical with a few authoritative servers on top level, a router or internet service provider provides information about which DNS service to contact when doing the lookup. Lower level DNS server cache mappings, which can become stale due to DNS propagation delays. Oh my god, bro, this is insane. I don't know. CDN. Content delivery network is a globally distributed network of proxy servers serving content from a location closer to the user, generally static files. content delivery network. Oh yeah. What's going on? Oh, we have another Krishna in the chat. What's going on? Krishna number 2. Globally distributed network. Yeah. You can configure when content expires. Sites with small amount of traffic. Sites with content that isn't updated often. balancer basically just distributes the traffic and requests evenly across servers. Having a single load balancer is a single point of failure, so we may want to do like a master-master replication or master-master replication. Can you do masters? You can do an active-active or active-passive on the load balancer. For load balancer, also need to consider basically load balancers distribute requests to sort resources at either the application level or database level. Okay. Resources. Helping eliminate helps so session persistence. Hmm. What's up? 3 years experience building full stack features. Yeah, that's cool. End to end. Okay, bye. Love you too. Content. So, CDN is basically, it's basically a way for someone to resolve the data. Before resolving DNS request, it will be sent out to a CDN, which the CDN will, which typically hosts like static content, HTML, CSS, JS, video files, JPEGs, you name it. We could also host dynamic content, but generally it is static content. We can consider that the CDN has two different methods of serving the content, of which includes content pull and content push. Okay, bye. Love you too. For content push, essentially, this is the most beneficial for. It is the most beneficial for sites that don't get updated regularly. So, for places where maybe there's not a lot of traffic, we can utilize it to serve the content, only serve the content as needed. The advantages here is that it does minimize traffic, but it will maximize the amount of storage we're using. But it will maximize the storage. Also, the other disadvantage here is actually that the CDN may not get properly updated if we have too many changes in the okay, too many changes in the server where the CDN is basically caching the data from. So if changes are happening frequently, then when the CDN serves that specific content, it may actually be stale. So then we have the push content method, which basically is best for sites that actually get a lot of traffic. So in this case, we may want to note that the disadvantages. How does the push content work? It basically fetches content when the user first requests it, and then it'll cache it. It utilizes the time to live or the TTL method, where essentially content will stay there until it is expired, in which case it's removed. Problem here is if a user will request data that has already expired, then it would, and if there is a lot of traffic, some people will, this will increase load on the CDN, which will decrease performance. Globally distributed network of proxy servers. It's a proxy server. It is. Serving content closely. Serving content. Generally speaking, load balancers have different ways of we can first of all, load balancers mate the single if the client connects directly to the application. Because what it does is the load to the database server that is available is for us to implement the load balancer using different these static server. We can implement the load balancer. It's, yeah, route methods or algorithms. So we can do which essentially just step this creates serious issues because if a database is What's up, dude? What's up? What's up, dude? Oh, you wanna come hang out with daddy? Wanna go hang out with daddy? Yes. 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 You're very handsome. You smell like dog. I think you need a shower soon. Do you want to go shower? Shower? Yes. You say I love you. Say I love you. Say you love me. You say I love you. You say I love you. Say I love you. Say I love you. Say I love you. Leo, love me. Leo, love me. Love me, Leo. Can you love me, Leo? Leo, love me. Come First proxy. Web server. It literally just serves the web, bro. Oh my god. I'm gonna name this proxy web server and the proxy. We have reverse proxy. Increase security. Is a web server. Load balancer. What's going on, Sharma? Bro is what?
welcome back to the channel. It has been a while since I've recorded, so I might be a little bit out of practice. One thing you may pick up on is my stunning goatee, which I've actually developed because I was getting hit on by too many baddies at the gym. I was getting distracted. It's a Saturday morning. It's some systems design. So let's get into it. All right. So a rate limiter. What is do? What is for? So I go browser. Well, YouTube doesn't also. So they say to me, guess what, buddy? You can't operate. We're actually going to stop you from watching videos. Which experience eventually the server is just going to be like, hey, you need to take a break. We'll tell you. Cool. So if I outline some form of requirements. So number one is that basically I'm going to build a layer that's going to stop bad users, malicious ones, or potentially just ones from submitting too many requests. Like I mentioned, I can easily bring down your service. You want to stop this from happening if you want extra service too. Additionally, this rate limiter should introduce latency, meaning we want to make it as fast as humanly possible. And every request has to go through this rate limiter, and as a result of that, we really don't want to be introducing extra latency here. It is going to kill our user experience if we do. Another thing is that there are a variety of different techniques, but most strong support at least a couple of those. And for what it's worth, at least from what I understand, there's some pretty complicated rate limiting algorithms. I'm not really going to go into anything too crazy here, simply because something as we get to the system design question, if you get cut in SDM things, the interview was like, you need to describe token and rate limiting. I don't know, seems dumb to me. I feel like it's more so the actual architecture of it, but we'll do a couple. Okay, so let's do some quick capacity estimates because this is going to be relevant in many fields.
What's up?
Like the connector from the mirror to this, so it's flipped down. So she probably needs a new mirror of the connector.
Oh yeah, so she'll just need to. Oh yeah, yeah, yeah. You could just buy a new one. Just buy a new one and then pull off the door and just put in the new one.
Yeah, so she's like the shotgun was sharp like 1200. So I was like,
Holy shit. That's doesn't make sense. You just buy the part yourself and then have them do the labor.
look, like NX 200T, but not just a T, not F Sport. We have the
It
same.
doesn't it doesn't it doesn't it doesn't matter. Like it can be a piece of shit Corolla and it should be the same price because it's not that hard to replace.
Yeah, she probably needed help or something.
Yeah, well, just need to order the part and then need to take some time to remove the door card and then remove the side mirror assembly and then just put in the new one.
It's a fun guy. Okay.
Not probably not today, but okay, yeah, I'll let me know. Okay, bye.
System. So let's imagine we got a billion users and using a rate limiter, rate for set. Imagine that we have 20 different services to rate limit. So when I say 20 services, that could be endpoints, authenticated or non-authenticated. So if you log in as a user endpoint, it could also be something like a rate limiter. So let's imagine that So assuming you or keep track of those bytes. That means at minimum, we're probably going to store at least 200 bytes of data. So keep in mind, we want to have latency here. If we were thinking about a solution, 240 megabytes is probably too big to be storing. Some service 56 gigabytes. Again, this was estimated. So again, if we are planning on storing memory, okay, so now we've got a more general question, which is what do we actually want to do on there? And we've got really a couple of options here, at least that make sense. Perform rate limiting anything, but it's probably better off performing rate limiting like the actual type requesting the game versus something that evaluates the user. So option number one would be user ID. The good thing about this is that it's pretty easy to track. It's probably fast request, and that malicious user can block that. That being said, it's not perfect, right? If I'm a user at home, accounts, the rate on one user ID is now not going to work as well. I'll basically be able to submit as many requests as I have accounts. Additionally, not all services need authentication. So if I have a login request and someone wants to DDoS that, I just spam the times and user ID to rate limit them because they're not logged in. They're trying to log in using a service. So I guess the fallback option would be the IP address. So the nice thing about this is that if someone is creating a bunch of accounts for the same network, it's easy to track. And in addition, it doesn't require the consent for actually the issue here is that you can have false negatives, basically saying I'm going to rate you, I've done nothing wrong, and it's my brother coming in. So you don't always want to have to throttle that person, but it's perhaps better to be safe than sorry here. So sometimes you do like the address. So ultimately, I think something like a hybrid approach makes the most sense, where you use the IP address for non-authenticated methods, and then second, so hopefully that makes a bit of sense. Let's quickly describe a rate limiting interface. So the gist that I mentioned is that we may have multiple rate limiting because they're going to have different implementations, what is the interface that actually describes how it works? So it should be pretty simple for the most part. We've got this function rate limit, which is going to return true if the refresh is throttled, or rate limited, false otherwise. It's just going to take the user ID, IP address, the user ID, I suppose, you're going to have that IP address, service name, so this would be like first, because every single endpoint should probably be rate limited separately. I suppose you can make the argument that you can rate user once, but I think it makes sense, at least for now, to do it separately. And then also a time of request, because typically when performing rate limiting, time between requests. I suppose that if it's a service where like you have an API key, you just stop them from making a certain parse total, because request domains or something like that, that would be a little different. But I'm assuming this is all going to be time based. Okay. So another question now that we have to ask ourselves in terms of discussing architecture here is where within our system does the rate limiter go? So again, we do have a load balancer, right? I'm assuming for now the load balancer and the rate limiter are separate entities. However, it is possible that if we want to make minimal network requests, we could actually put our rate limiter on our load balancer, right? Well, maybe not, because we mentioned that the amount of data that we need to store is probably going to be too big to keep in memory, thus making it infeasible for our load balancer. Could we put it on our load balancer's hard drive? Maybe, but then now you've all of a sudden disk access, and that could potentially be very slow. You don't always want that. So option number one is we can perform the rate limiting locally on every single service that needs it. So imagine we've got like a post service, get comment service. You would actually store in memory some data about all the requests the users made, so that you could go ahead and perform rate limiting locally on the server. So that's option number one. Two is going to be dedicated distributed rate limiter. So that would mean that rate limiting basically has its own layer in our system. So we'll talk about the pros and cons of both, starting with the local limiting. So I'm going to just call this service local rate limiting. I don't know, so maybe don't use it in this video, but makes sense. So the pros of this should be somewhat clear, which is that there's no extra network calls required. Because all the rate limiting is done right here on our service, we can just keep that data locally. As a result of doing so, we can share. Okay, so no extra network calls. However, there are some cons besides the fact that to actually manage a distributed rate limiting layer. Number one is that if we're getting spammed over and over again, this is a really big point, those requests are still making it over to the service, right? So that's going to use up a bunch of network bandwidth. We don't have a separate layer that's going to be managing those requests and making sure that they don't get run over service. Okay, so that's one aspect of things, which is that so server network bandwidth. Another one is basically application and actual scalability tightly coupled. So what I mean by this is, let's say that this amount of storage right here is not enough. So we need more rate limiters, right? And now to create a second replica of service one, service replica two, just to store all of the rate limiter information. And to be honest, that might not necessarily be useful, because who knows, we might just not need that much capacity in terms of dealing with all the service one requests. It just so happens that because of the need to make a multi-rate limit, that we have to scale it out a little bit more than necessary, which is not necessarily that useful. And lastly, of course, if one of these guys were to go down, we lose the rate limit information with it, which is not the end of the world. So we could just continue rate limiting this when it comes back up, but it is worth noting that happens if it goes to a dedicated distributed layer. So let's go ahead and talk about that. So here we would have a load balancer, and basically on every request, we would first reach out to the rate limiter. The rate limiter would say, okay, this request looks good, I'm not rate limiting it. And then number two, we actually reach out to our service. So what are the pros and cons of this type of approach? Well, the biggest pro is that we actually shield our application servers from the intrusive network traffic. I'm spamming, spam. What's going to happen is the rate limiter, instead of saying okay, is going to say no, you're not getting through to us, there's nothing on our service. Now, of course, these are still going to hit the load balancer, which is shitty, but eventually there's not really much you can do about that. So again, again, that's one aspect of it. And then another thing is that we scale this down up or down. So if I need more space for my rate limiter information, I can just do that. Partition this by users or something, and our load balancer can keep track of which rate limiter to actually reach out to. So again, that is totally doable, and then instead of service, we don't necessarily have to make for it. So, of course, the bad part of this is that now all of a sudden we have to make an extra networking call to the rate limiter. It's going to slow us down. We don't want that. Well, what could we potentially do to make our life easier? One thing that we could possibly do is actually do some caching. We do it well in a place that is going to allow us to avoid an extra networking request, which in this case would be load balancer. So what could we do? Well, basically we can have the load balancer effectively be a write back cache. And what I mean by that is that after a certain point, the load balancer basically acts as a partial rate limiter itself, but just not for every single user ID, only for certain user IDs. So maybe if we have a rate limiter of 10, what we could say is that when the load balancer receives from the rate limiter that there is someone who's made 5 requests within a certain time period, that it'll actually cache that value. So now all of a sudden it's storing that I've submitted 5 requests. As you can see, it's going to store that over here, cache it, and the next time when I reach out saying, hey, can I make this request? It already knows that I've made 5 requests. It can locally add such that now it sees I've made 6 requests. It could say, okay, I can reach out over here. So this will ensure that certain particularly spammy users aren't even making their way up the rate limiter, but are just getting rejected on the load balancer. Again, it's not really even important that stuff is getting written back to rate limiter, right back cache, assuming there's only one load balancer. If we're using something like an active load balancer configuration, then we may run into a few more problems. We have to be a little bit smarter about how we'd actually partition our request to load balancers or something like that. But assuming there is just one load balancer, this approach can work very nicely. Okay, so let's now discuss our database choice. So we know that our rate limiter is going to be a separate service. The question is, how can we basically set this thing up to be as fast as humanly possible, but for the things it writes, because otherwise we're really going to be slowing down every single request. So the idea is we want them to be as fast as possible, and as a result, we probably don't have to access disk. When you want to keep things fast, disk really can get in the way. So what can we do? We could just keep all of our data in memory. So that would naturally lead us to either A, just using a custom application server solution, or B, employing something like Redux and Cached, which are both just in-memory databases. So personally, I lean towards using Redux here just because it's got some existing data structures that we can use, like a list, and then also as far as setting up replication goes, there's not much that we have to do on our end. It takes care of a lot of that for us. Pretty easy to get single user replication going. So I personally am leaning towards Redis. I think if you want to make the argument for any other database that stores stuff in memory, that would be the best. Okay, so now let's talk about our replication choice. I guess the question is, can we get away with using something like multi-meter or replication here? That's a good question. At the end of the day, we do need our rate limiter control following, because if one goes down, that would mean all of a sudden we can't submit any requests to a service, and that is not acceptable. So let's think first about multi-meter replication. Imagine we have multiple rate limiters, basically multi-meter setup, both communicating with one another. First of all, that could increase our write throughput because now it's completely interacting throughout the coast, and additionally could even decrease our write load on each of those databases as a result, because you just have more places that I can write. At the same time, though, let's say rate limiter is being stored at 3, and this guy is stored at 2. We need some time for them to actually sync up. We have to wait for the entropy, and there's not really any guarantee that that will happen. Another aspect of things that we can do is use a CRT. So again, this would be more of like a version vector almost of counts that I've done. So this guy would say, I'm replica 1, so I believe that I've received 3 writes, and replica 2 says I've received 2 writes. So basically my count is 2 locally, and my count is 3 locally over on the left here. And when they sync up, this vector becomes 3, 2. what a CRD key is. It's basically the idea is that you hopefully the right answer when they eventually sync up with one another. They do so in a way that doesn't cause any write conflicts and can actually get the total instead of some improvements. Even still, again, I think it just be accurate in rate limiting counts from the get-go. And the way that we could do that most easily is by using a single leader. So again, if we just have a single master node over here, it's got something like a follower. I write to the master node. This is going to be asynchronous over here to the follower, and then I can always just make requests as well. And if this guy goes down, then this guy becomes the master. Now you may be saying, well, what if we read from followers? We could, but we might get stale reads. And then you might say, well, shoot, now the master is going to have very high read load. And you're correct there, but I guess we could just create a sufficient number of partitions such that hopefully that isn't an issue. So that is my thinking there. But moving on, now hopefully we can get to the actual meaty part of this video, which are a couple of the algorithms that we want to be covering. So I'm going to be talking about two limits. There's fixed window rate limiting, and there's also going to be sliding window rate. These are relatively basic. I've actually spoken about these types of things in a stream processing video. So if you need more detail on this process, you can watch that. But the idea here with fixed window rate limiting is basically that we have a certain rate limit, let's say it's 2 in this example, and that it resets every single basically discrete unit of time. So in this case, let's imagine that it resets every single minute, starting from clean minute. So for example, that means that these two requests are valid. Now reset. So these two requests are valid. Oh shoot, this one comes. So that so to keep this in mind, imagine we're storing data structure, right? There's some map, service name, which is going to be upload, user ID, which is going to be 22, to basically the current time and counter. So at 1 o'clock, so now you've got 0 requests. So this guy comes in, all of a sudden we've got 1 request. This guy comes in, we've got 2 requests. This guy comes in, here we have 1 request again, but the time is now 1. Same thing for the next guy. Now we've got 2 requests, the time is moved up. And then finally, this erroneous request comes in. This comes in, the counter gets set to 3. You can see that is bigger than 2. And so now all of a sudden we have to actually clone. So hopefully that makes sense. I'm going to go through the actual pseudocode for it. No worries if the inputs just made sense. The pseudocode doesn't.
Fuck. Do I have to do pseudo?
Hello there, and welcome to this system design mock interview. Today we want to show you a really high quality, best in class system design answer so that you can use it to prepare for your interview and use it to know exactly what standard you should be aiming for. With us to give us the answer as the candidate today, I have a former engineering manager at Google. It's Mark. Mark, how are you doing?
I'm doing great, Tom. Thanks for having me. I'm looking forward to doing this.
Thanks for coming on. It's great to have you. Before we get started, just want to quickly give people an idea of some expert feedback. Spotify.
So yeah, so Spotify is probably one of the most popular music streaming services out there. So let me think about that just for a moment. Some notes. There's a lot of aspects to Spotify here. Let me see if I can actually, maybe I'll just take some notes here so that I can kind of think through this, if that's okay, and make some assumptions. So I have some notes. I'll just put this right in here, and then if it's okay, I'll just use this for notes as well as sort of the design diagrams and things like that later on.
Yeah, sounds good.
So let's talk about some different. So Spotify, okay. So for Spotify, I can think of things. I mean, obviously there's songs, music. That's the main thing. There's you have playlists. I mean, there's users. There's artists. I guess Spotify even has things like podcasts, listen to things like that. So there's a lot to it. And so in terms of the system design for today, uh, there, like, can we constrain this a little bit just so that we can actually get through a design? What we get to focus on here?
Yeah, let's constrain it. Let's limit ourselves to, let's look at finding and playing music.
Okay, okay. So let me, so use cases, write it down like verbatim here. Great. Okay.
Enough to talk about.
So yeah. Okay. Good. So I think that let me try and the use cases a little bit more. So my typical use case then as a user, if I'm signed up to Spotify and I have an I'm going to browse some music. Maybe I'll find a particular search for a particular song, but then the most important thing is that I play a song and it's coming back through my phone, maybe my car or whatever, wherever it might be, headphones to listen to it.
With big, broad questions like this, you need to constrain the problem, make it solvable in space for now. And Mark did this well, establishing the use cases we wanted to focus on. Share
Other metrics here. Let's think about size. Let's do some quick drilling down into some numbers here. And some numbers. So tell me about users you're thinking about here for this design.
Yeah, let's say 1 billion users.
Okay, 1 million users. Okay. What about songs?
Yeah, I think I saw somewhere that Spotify has about 80 million songs, but let's say we need to have capacity for 100 million.
Okay. All right. So 100 million songs. And we're going to focus on the song piece of it. So let me do a little bit of math here, a little bit of thinking, and I'll just I'll double check with you to make sure that this makes sense. But um, when I think about a typical MP3 audio is going to be about, for a typical song, is about 5 megabytes. And I mean, I think that it depends on the encoding of the song, how long the song is, and things like that. But if that's okay, we can just kind of make that assumption. Is that fair?
Sounds good to me.
I think you can encode these things in, like 96 kilobits per second, all the way up to 320 kilobits. But right in the middle, 120, 160 is about maybe about that. So, all right. So let's assume that. And so let's just extrapolate from this. So you got 5 megabytes per song. You've got 100 million songs. So I think that translates to, I'm trying to do my math here. So 100 million would be going to 100 billion, and then 100 trillion would be a million times. Times 5 would be 500 trillion. So we're talking about total audio is something like 500 terabytes, which is, I guess, it's the same thing as a petabyte of data. And so I'm making that assumption. And so then, depending on how you replicate this data, because you typically want to have these songs in multiple copies of these things so they don't get lost, etc. And if some replicas down, so maybe say, oops, so we'll get 3x replication. So that would mean like 1.5 bits of raw audio data. And and each song, in terms of the metadata, meaning the song title and things like that, and artist and all these things, the metadata is probably not very big. It might be 100 bytes per song or something like that, per song metadata. And so you might wind up with, okay, so let me do the, that's 10 billion. So that's only 10 gigabytes of song metadata. It's not really very much. And even if you say it's a kilobyte and that's 100 gigabytes, that's very much. Let me just double check my math here. 100 million times 100, really 100 bytes. Yeah, I think it would be 10 gigabytes. So even if we said, if we rounded up dramatically and said 100 gigabytes, that's just not a ton of data. Now, in terms of users, data you might have, again, maybe a kilobyte, kilobyte per user metadata. It's a full metadata. And so that might be times a billion users. So that would be a terabyte. So just be doing some quick metrics, quick calculations to get a rough back of the envelope of how big these things are.
Yeah, that all makes sense so far. Before starting your high-level design, as Mark did, get without getting bogged down in heat neat.
So let me maybe think about some basic components here. I'm going to draw them, but I'll get into them maybe a little bit more in detail later. So some basic components I would see. So let me start with something that is my best attempt at a mobile phone here. So you have your Spotify app. So it fits. So you've got your app, which is on your phone typically, and I'm going to assume here that we're talking about the phone app because that's very common. And so you've got your phone. The phone is going to be talking to an application server, Spotify application server somewhere, web server, I guess. And so let's draw some. Let me just put a. Let's just say there's a web server, and there's not going to just be one. There's going to be lots of them, and assume that that's a lot. And then, of course, just because this is a standard thing that you do when you have applications, in the cloud here, this is, I guess, part of the cloud. You've got a load balancer, and so let's assume that we've got an arrow here that's talking. So Spotify app's talking through the load balancer ultimately to these web servers. And so those are some sort of key components here. Let me think about this a little bit further. Yeah, that's good so far. Okay, and then of course, the most important thing, one of the most important things here. Let me see if I can find a. I know that there's a shape here. Here we go. That's a good shape. I'm just going to say call this the database. That's what. Okay, so there's a database, and so the web servers are going to be talking to the database and getting stuff from basically reading information, writing information to and from the data, reading and writing information to and from the database. So those are kind of the very high level components.
In system design interviews, good dual bandwidth communicator. You should practice this quite early in his answer at this point too.
Yeah, I think this is obviously oversimplified, and redesign Spotify existing full application that exists, but I do think I can get a little bit more detailed here by the data again, because it's the data is important. So I'm thinking about the metadata and the user data and the audio data. So I'm going to split this up and say that there's a audio database, and then there's going to be metadata. So this is users. I mean,
You just bombed an online interview round today and couldn't sleep. Damn, dude. That's really unfortunate. But hey, part of the process is just to keep interviewing and get used to what you're expected to do during those interviews, right? You'll for sure eventually strike gold. So, or maybe not gold, maybe just like bronze or something. But we take what we can get. Sorry to hear that though.
Art, ultimately, there would probably be artists and et cetera, things like that. We were focusing on songs that they could write music. And so, and this is also database, of course, song, audio, and so I think let me the Spotify web server is actually going to talk to this to the metadata and audio database. So it's actually going to be talking to two databases here.
Yeah, that's interesting. Can you into a bit more detail about why you split them into two?
Yeah, assuming that I'm making that. Yeah. So okay, let me to try and I want to let me try and think of this in terms of the technologies that I might use. I might use something like Amazon S3 here, and I might use Amazon RDS. And so now let me explain what I mean by that. So the type of data, the actual MP3 files, those I think of as immutable data. They're just blobs of data. They're files. They're 5 megabyte roughly, an average files, and they're not going to change. They're just being streamed. They're being stored and streamed essentially. So a blob database, which is what S3 is, lends itself really well towards that. And it can be something like Google Drive, or there's other technologies that are sort of just document like blob storage systems. But Amazon S3 lends itself really well to that, and it scales greatly. You can just add more and more and more and more, and it scales linearly, which is great. And so
Hey, yeah, so this is a Google engineering manager. He's doing a mock system design interview about creating Spotify. And I spent quite a bit of time trying to get used to the terminology and just kind of the basics, but I think it's time for me to start studying these mock interviews to see kind of what is expected. Like, in this specific interview, it looks like what he did was he talked about what the application does, and then he wanted to narrow down into the specifics because obviously building a system for all of these specific I guess like use cases, or not use cases, but um, features, right? So building a system design for all these features is just not feasible in a matter of like 30 minutes to an hour. And then he specified, well, okay, if we're gonna specifically talk about songs and music, they're also gonna have to be certain. The use case here is literally just for a user to go find a specific song they're looking for and to play that music. He then went into the metrics, right? So he specified, how many users are we dealing with, how many songs are we dealing with. He gave a really rough estimate of what an MP3 audio size would be. And then he calculated the space it would be required based off the songs and the size of the audio file. And then over here, he's thinking, well, obviously you're going to have a web server that, or not web server, but you want more storage available than the minimum amount needed to handle the songs, right? Because obviously more songs will be added over time. And so he basically calculated based off the replication of 3x 100 million songs, you would need about 1.5 petabytes. He then specified, well, each song has specific metadata like the artist name, the album, the date it was released, and the what album that song is a part of. So he, basically said, well, there's 100 bytes probably roughly of metadata, and he went ahead and did the same thing with users. So after calculating the metrics, he's now doing a rough design just kind of a high level overview of what it would look like, and then he'll probably drill down into building more in-depth, specific like components for each part of the system.
And then you can connect it up to be able to stream the data and things like that. So that type of data and the access pattern for that, which is really mostly read, you're just streaming this data. You're never going back and forth and writing to it. That would be why I would want to put the songs in kind of a database. Now, S3 is great for that. Works really well. The data, the metadata, which is the information.
The role was quite different. This was an AI intern role at an investment bank. Oh yeah, dude, AI is like super math heavy. Um, I'm actually like kind of not surprised about that, but um, yeah, AI is like extremely math heavy. I would say it's almost on par of like being a graphics engineer. Those are usually also extremely math heavy, like linear algebra and stuff like that. Like you can know the theory, but you also probably need to know the like how those algorithms are used and how to solve a particular problem using those algorithms is my guess.
And the songs that are information and maybe they get updated. Maybe you're searching across them and having to do queries to find some particular genre
Sort
or
of quant. Right,
artist
right,
or
right.
things like that. You're trying to update your users, like playing a song and where I left off, so that when I continue playing, it remembers that. I'm going to be modifying the data quite a bit, or going back and forth between that database and doing these queries. And you can't really do queries over S3, but you can over like a relational database. So MySQL would be another option. Um, I just chose RDS here, Amazon relational database as a AWS family here. Um, but yeah, so uh, try and try and just in terms of songs, you would have things like a song ID. You would have a song if you use sharing. You would have a genre. Maybe there's a link to album cover. Maybe there's a link to the audio, I guess. So this is the type of data that would be stored in here again, like in that database, and then just the raw. I mean, I almost don't need to write this here. So song MP3 would be stored in this database here. So yeah, so I think that the access patterns, the types of things that you want to do, the size of the data, because the size of the data here, I think we said was going to be, well, petabyte in one for one replica. So S3 lends itself well to that. The data here is going to be, in the maybe terabyte range, something like that. And it's going to have lots of queries over it, maybe some updates and things like that. So that's why I would separate these out, is because I think the access patterns, the size of the data, and the type of queries that you need to be able to do would be very different. Does that make sense? Does that answer?
Yeah, it does. Thank you. Yeah, I think that makes sense. At this point of your answer, when you relate it with the data, for it to continue,
And I'm just trying to think about now the actual the use case. Sorry, the use cases we talked about. So finding and playing music. So finding music, I think the Spotify app, would need to request do a find music. So the user probably, either is typing in like an artist name, or maybe they're selecting a bunch of filters. I actually am not how possible that is, but let's say I'm searching for music for an artist with a particular genre. And so ultimately, someone fills this query in my app, either by clicking on some things or typing some things or a combination. And then that request to find music is going to be sent to this web server, going through the load balancer, pick a web server, it's going to go there. And then that web server is going to do a query, issue a query, a translated query to the relational database to find a bunch of songs and return a list of songs and return that back to the app with whatever metadata there is. And let's say that I found it finds, I don't know, 100 songs that match my request for music or something like that. And so I now get back 100 songs and I can look at those. And now, once I've gotten that list of songs, and by the way, for that query where I'm searching for music, I don't touch the MP3s at all. I don't need to go to that database at all. I just need to go to the metadata database and do this query. And because it's a relational database, that query can happen pretty efficiently, etc. So now I return that information back, and then I display that to the user. Does that make sense in terms of finding music?
Yeah, yeah, that makes sense. That's good.
Okay, and so now I have a list of songs, and maybe there's like one of the ones in that list is like, oh yeah, that's what I was looking for, and so I click on that song to play. I want to hear the song. So that's the second sort of part of the use case that we talked about, just playing music. So to play music, now this gets a little interesting. This is, I think I'm going to wind up maybe changing what I'm thinking about here a little bit, but let me just talk through it. So I click on play button, or I click on the song name to play it, and that translates into a request from the app to the web server to start playing a song, playing the song. It has an ID, like I mentioned, has like an ID.
Is this grokking the system design? I don't believe so. This is I got an offer engineering, and it's just the Google system design mock interview. So it looks like key points so far is to narrow down the specific use case, or the specific feature that you're focusing on, find the use case that you're specifically going to build the system based off of, build the metrics, and then you build a high level overview of the system, and then you start to drill into the specifics like what metadata it contains, and what this database contains, all pseudocode. Um, yeah.
In it, and the web server, based on that song information ID, has to go to this database here to look up the link. What did I call it? Oh, an audio link. Maybe that's an MP3 link. I don't know, something like that. So the MP3 link, and so that MP3 link, audio link, would be returned, and now the Spotify web server has to go to the database where the actual audio is stored and fetch that database. Now, you could imagine streaming that 5 megabytes from this database. So chunk by chunk, it comes back, and chunk by chunk, it goes up to the Spotify app. In order to do this, you need like a WebSocket connection. So you need a kind of a long-standing connection between the application and this web server, so that you can send the data back in chunks. But I'm not sure whether because it's only 5 megabytes, that's possibly small enough to just fit in memory. Read the S3 and fit into memory, and then have that particular web server chunk it back from there. I think that might be better because it would eliminate the possible lag between the database. So you don't start streaming the audio until you have it in memory. That might be something that I would consider doing. So, that would be. Does that make sense? Like playing, like you start playing, and now obviously you can control it, you can pause playing and so on, but does that make sense? So you start playing, the web server gets the request to play, it maybe gets the information about where to go over here to
Dude,
get to
online
the
assessments are rough, dude. I totally feel that.
storage, audio storage, reads that back. It's only 5 MB, so it should not take, it should be almost instantaneous. And then it starts streaming that back to the application. Does that make sense?
Yeah, that makes sense. Please carry on. So all good so far.
Okay. So, so it sounds too good to be true, or sounds too easy. It's got to be more complicated than that. Okay, so one thing I'm just realizing here is probably out of these, what did we say? We said 100 million songs. Uh, there's there's probably a lot of stuff that is the term indie artists or something like that. Stuff that few people, not very many people listen to, isn't very popular. And on the flip side of that, I'm thinking about like what could go wrong here. Well, if like BTS, which is a Korean band, uh, if they, let's say they release a new song and it's like, hey, everybody wants to listen to this. This is super. Oh, have you heard this song, etc. If you've got all of these web servers all fetching that same thing, that same song, and let's say you've got, requests like it's released, and in the next minute you've got, I don't know, you said a billion users. Okay, let's say that 10 million users all request the song all at the same time or something like that because it's just been released and the social media is something. You easily overload in terms of bottlenecks. You could overload possibly a bucket, or that bucket, excuse me, that particular um, song, that file or whatever, how it's stored in AWS, and it could be stored different ways. I'm using S3 here. You could overload AWS or S3 there, and you could also possibly be, like streaming, like loading up all of these web servers with the same song, streaming the same thing back. So it's a lot of bandwidth, etc. So better thing to do, common thing to do for stuff like this is to use what's called a CDN, content delivery network, which is like it's a cache. So this helps reduce the amount of load on backend. So let me draw something here. Pick, so maybe over here. So I'm going to say here, this is a CDN, which is an video cache. And so
Yeah, CDNs are pretty badass.
so, by the way, technology
You
is
you
here.
literally closed the laptop and went for a walk.
CDN.
Oh, dude.
Very,
There's one time I don't even remember what I failed, but I think it was I interviewed for HackerRank, and like I just got restarted in DSA because I hadn't touched it in a long time, and for some odd reason, it was structured in a way where it looked like you were doing a practical programming exercise, but there was like leak code built into it. So it kind of threw me for a spin, and I can't remember the exact question, but I remember that I looked at it and I could not figure out for the life of me how to solve it. I typed in a bunch of random solutions and nothing was working. And the crazy thing is it builds off of the previous solution, right? So there's like multiple steps to it. And so the first solution I did it with, I think I used like a hash map or a set or something. Um, and then in the second step, it was building off my first solution. So I couldn't go back and edit my first solution. I had to build a second solution, or I had to solve the second problem off of my first solution. So it's structured in a way where like if you fuck up in the first section, you're actually kind of just boned in the second one. And I just couldn't figure out a way to solve the problem. I literally sat there, I looked at the time, and I was like, yeah. So I basically just got up, I went in my car and just went and picked up some beer. I was like, fuck this, dude. But yeah, like it, yeah, it's rough, dude. I totally understand. It's crazy.
Very close in terms of number of hops and network connections to users. So what would happen is, let me draw another arrow here, and let me draw an arrow down to here. So what
You used all the AI tools and none of them can pass test cases. Isn't that the whole point, though? What the fuck?
the first time that this song is this new BTS really, really single is requested, the web server would read it and stream it like normal, but probably we need to make sure that these Spotify web servers are somewhat, they're keeping track of things. And they're keeping track of, which songs are being requested, which ones are hot. They probably have a heat map of the most recently requested songs.
Oh yeah, yeah,
So
yeah. I've seen that.
they see, oh, this song is now, I've seen this requested the fifth time in, in a minute or something like that. At that point in time, what it might do is it might actually, instead of just streaming it back to itself or copying it back to itself, excuse me, it might actually load that into the CDN. And so I'm trying to draw another arrow, I think, in order to do that, because these things probably have to talk to the CDN. And by the way, I'm not a super expert on this area in terms of how this works, but there's some connection between this edge caching, this content delivery network, which is just there for caching, and these Spotify web servers. So these web servers are going to somehow notify the CDN, hey, you should be pulling this song.
Just scrolling and saw the live stream. Hey, thanks, gifted fingers. I appreciate it, man. Doing pretty good myself. How about you?
So the CDN, would load that up. This now has to work in conjunction with the application. So that means that the application, when the person decides, when I request a song, I want to play this latest BTS song, and it's just been released. Before I go and I talk to the web server, I might even go and check in the application might actually go and check in this content delivery network to see is it there. It might also be, so if it is there, then I just read it from there. The other option, the possibility, and again, this is technology that I'm sort of not super familiar with, is that it goes and asks the web server just like it normally would. And the web server sends back a redirect saying, hey, I don't have it, but you should go over here to this content delivery network, this edge cache, to fetch the song. It's much closer to you. You'll get better performance, and you won't be loading me up so much. So I've got a lot of arrows here. the standard flow for a song first time around is, coming around, getting the metadata, going around to reading the audio data. The web server is now keeping track and realizing, oh, you know what, I'm getting multiple requests for this same song. Now I'm going to tell the CDN, go and fetch this song. It's going to fetch it. And so now the application can be redirected, for example, to read that audio from there. So that's a lot of talking, but I was realizing that caching here seems like
Machine learning based auto scaling for AWS.
design.
That's crazy. That's beyond my scope, dude. But that sounds intense.
Is that
Absolutely. Yeah, that's a really good answer.
Okay.
Yeah, so um when you prompt your AI tool enough, it passes a lot of test cases. Yeah, I mean clearing OAs is tough, dude. I've failed a lot already, so I haven't used any AI tools yet. Don't know if I will, but yeah, I mean, I think what helps me is usually drawing out the problem and then trying to dissect it on paper. Just because I don't know. I don't know, man. These interviews are crazy, bro. I wish there was just a way to get certified. Just be like a certified software engineer and just not have to deal with all this insanity. But it's fine, I guess.
Again, in the AWS family here, I'm going to use the family. You know, obviously, if I were Google or I might not be using this, but there's a technology called CloudFront, and CloudFront is basically a content delivery network. There's a bunch of other ones. Flex, is that what it is? I can't remember what the names of these technologies are, but there's a bunch of other technologies that are very similar in nature that allow you to do this. So that would help with the bottlenecks. And in terms of the caching here, you could also, and this is part of the reason, by the way, I'm just stepping backwards here a little bit. Part of the reason why I think it would be better initially when the web server is getting the song for the first time for it to read the entire MP3 into its memory, because then if it is getting multiple requests for a particular song, it doesn't have to go to the database. It can actually just feed it from its memory, and that's also a form of caching, of course. So it's got a local cache essentially of 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 these songs. And you can imagine having a shared cache that's shared across these web servers. So that could be another optimization. But my point is that if we have a cache in memory in these web servers that stores the songs, then we're offloading the database a little bit. If we then have the cache here at the edge of the network, so it's edge caching, then offloading the web servers uh, to a large extent because the streaming, this is optimized for streaming and so on. And I think if we go one step further, actually, I'm, I'm sure, and if I were designing it, I would design the application as a smartphone to store the songs that are played frequently by the specific user locally in the store. So it's another form of caching. So then, if it finds the song in its local cache, essentially local store here on the phone,
Continue DevOps course. Right on, bro. Good studying. Good luck studying. You know, work hard, work hard.
Cache, little local storage here of songs. So then multi-layer caching, just what I'm saying. Multi-layer caching provide the best user experience, make sure it's super fast, and to then offload obviously the system to allow it to sort of scale and limit costs, etc. So that's probably enough of a caching. Gone deep a little bit there.
Are you ready for the interviewer to ask you about particular components or different aspects of your system? And to talk in the purpose
balancing a local cache essentially
Oh man. Heading off to watch anime. Enough tech for today. Cool, cool. Sounds good, man. Take care of yourself. Sounds good, man. Thank you for the subscription, bro. I'll see you in the next stream. Hmm. Design.
Back to and in this series, we're going to break down today. So today we're going to design Facebook Live. That's actually the second most popular question. So as always, before we get into the actual design, let's take a moment to go over this video, and it's the framework that I recommend that you use in your system design. And so if you've watched any of our other videos, you've seen me do this 100 times, you're tired of it, feel free to pause it. Framework, we're going to go through these 6 steps. First off, we're going to outline the requirements of the system. And so this is your opportunity to make sure that you are on the same page with your interviewer about the system that you're going to build. This includes what we call the functional requirements, or the core features of the system, as well as the non-functional requirements, or the qualities of the system. After that, we're going to outline a very basic list of core entities. And so this can be thought about the nouns of your system. Oftentimes this correlates one-to-one with the tables in your database. But we're going to stop short of outlining the full data schema or modeling any relationships. The justification being that we just don't know it yet. It's too early in our design. But we do want to outline the nouns because they're going to give us the context necessary to understand our API and then move into our final design. And so once we have this core entity design, as I said, we go into the API. This is where we'll outline the core user-facing APIs, and we'll exchange those core entities that we outlined in step 2. Now from here, data flow, this is for infrastructure-heavy system design interviews. You'll need to decide on the fly whether or not it applies. In this case, 1, and so we're going to jump right into step 5, which is the high-level design. The high-level design is the part of the whiteboard. We start drawing boxes and arrows in order to outline a very simple system where the goal is to satisfy our core functional requirements. So in this case, we're not going to satisfy the non-functional yet. Our system might not be able to scale. It might not be low latency. It's very basic, but it's the minimum required system in order to satisfy those core functions. So we'll get that down, and then we'll move on to step 6, the deep dives. So this is where things get interesting. This is where senior and particularly staff candidates show their work. And this is where we go one by one through the non-functional requirements that we outline in order to expand upon our design, our original high-level design, in order to make sure that we satisfy the non-functional. This is where we'll handle the scale, the latency, security, anything like that. So that's how I'm going to look. Let's do that now. Before we get into our first step, which will be the functional requirements, let's just take a really brief high-level explanation of FB requirements. So you're probably familiar with Facebook Live. Facebook Live is a feature within Facebook app which allows users to live stream videos from their audio.
Oh, my back.
Now, what we'll do is under that live stream, this is where we do a comment that gets streamed in real time. So as users are watching the video, they can be posting comments and they're waiting for the video to stop. To all other users with it in real time. And so of course this is not exclusive to Facebook. This is true of TikTok Live, this is true of Instagram Live, this is true of Twitch, YouTube Live, any streaming platform. So the solution that we're going to have here applies to any of this. Awesome. Okay, so let's get started with our functional requirements. As I had mentioned, the functional requirements are the core features of the system. This is where you're going to agree with your interviewer. Now in our case, the core features are relatively straightforward. I'm going to place them in because it's going to be better than you guys watching me struggle through typing video. But the core functional requirements of Facebook Live comments are first, most obviously, users or viewers need to be able to post a comment. That's crucial. Fantastic. The second is that viewers can see all comments posted in near real time. And so as new comments are coming in, we're appending those comments to the bottom of the list so that users can see them. Importantly, without having to refresh their page. And then third is that you should be able to see all the comments that were posted before. And so maybe in the case of Facebook Live, TikTok Live, this means that you can scroll up when you're reading comments and it'll load for older comments that you can still read. Those are your requirements. Now I put some things below the line here. These are things that would be reasonable in an interview like this, but are out of scope for us. That's the ability to reply to comments and the ability to react to comments or even just react to the video in general. And so one thing to note about this below the line thing, don't feel obligated to do this in your interview. My suggestion would be to use this technique of below the line only if you're in the process of brainstorming and something comes to you that you discuss out loud and they agree with the interview. So if you're thinking and brainstorming about the functional requirements and you say something with the interviewer, well, should users be able to reply to other comments? And they say, let's consider that out of scope. Then that's something that you can specify that's below the line. Basically a contract between you and your interviewer. These are the things that I'm going to focus on. These things. Next up are those non-functional requirements. And so non-functional requirements are statements about the system's qualities that are important. And so they can be phrased like the system should be able to, the system should be statements. So for example, if you're designing something on Twitter, it's like the system should be highly available.
How would you design a real-time messaging app that can support millions of users?
Let's see an actual mock interview though.
So the system sounds good. So Telegram is a in essence a messaging application that allows users to send messages to each other and even to groups of people. And it's very scale. There's a lot of big scale, so a lot of users on this application, and so I guess for purposes of this interview, let me kind of ask you some questions about this. Make sure that I really understand what you want me to design. This Telegram is pretty big, it's pretty complex, it's sophisticated. So let's kind of see if I can narrow this down and ask you some questions. So Um, first off, in terms of use cases, again, I mentioned it's basically about sending and receiving messages. And so I think the primary use case that I want to think about is I want to send a message and I want to check messages and read my messages. There's also sort of groups. And so maybe a question to you is, are those the basic use cases that you'd like me to cover in terms of the functionality of the system? And what about groups?
Yeah. So yeah, I think that's right. Let's go for sending messages and receiving and reading messages. I think we can leave groups to one side just for the purposes of the interview today. Just with the time that we've got, let's forget about groups.
Okay. Okay. So for now, just kind of one-to-one messages makes sense. And so then, in terms of these messages, for just kind of make an assumption here that we're really for now we're just talking about text messages. They can Telegram itself allows you to send larger things too, but for purposes of this, is it okay if we just kind of talk about sort of messages, text messages, sending or receiving those?
Yeah, that's fine. Yeah, let's stick to that.
Okay, sounds good. So let me ask you then a little bit about. Okay, so hang on. So in terms of the functional requirements, so sending, receiving messages, what I'd like to do as I'm going through this, if that's okay, is I'm not really much of a front end person. I'm sort of work more on the back end side of things, and so I wouldn't be able to speak a lot about sort of how this shows up in an application. And so the entry point into the system might be APIs essentially, and I can think of 4 APIs which we can go into a little bit later that might reflect that. So I wanted to check with you, is it okay if we sort of use APIs as the entry point into the system design?
Yeah, that sounds fine. Fine for me. Mm-hmm.
Okay. So then let's talk about, I think those are the functional requirements. Let's talk a little bit about non-functional requirements. So I think the one thing that I think about a lot when it comes to non-functional requirements is scale. How big is this? Do we want the system to be? And so maybe tell me a little bit about what kind of scale, how many messages do we want to be able to handle in the system?
Yeah, good question. So let's assume that we want to be able to handle 10 billion messages sent every day. We want to be able to double that in, say, a year's time.
Okay. All right. So that gives me good hints about some core ways to think about the system. That's useful. Thank you. And then in terms of, all right, so if we say 10, let's use that number just briefly. Let me do some quick math here. Think through this a little bit. So if I think about 10 billion requests or messages per day, and you're talking about sent messages being sent out per day.
Yeah.
Okay. So 10 billion messages sent out per day. So if I think about that in terms of transactions per second, because ultimately, servers need to handle things sort of in the moment. There's roughly 100,000 seconds in a day. It's not exactly right, but it's close enough for our estimation. So at 100,000 seconds in a day, 10 billion requests per day, that translates to about 100,000 messages per second. And if you then take into account, maybe peaks like during the day, um, let's just say 500,000 requests per second or so. Does that seem reasonable? Does that seem okay?
Yeah, that seems accurate. Yeah, I think that's it. I think that's the right ballpark.
Okay. And so then, as you said, doubling in a year. So that would mean, we'd be able to handle 1 million of these And so really what this translates to is we need to be able to horizontally scale the system. So again, that's good hints. And so if I then think about just roughly a servers that might need to be able to handle this on the front end, but we get to that detail, but like a server might be able to handle a typical server 10,000 requests per second. So just ballparking this, maybe 50 servers to start with. And if we do this in a way that allows scaling automatically, elastic, allows some scaling, elastic, but sort of elastic growth or whatever you want to call that, some right term. Scaling, automatic auto scaling, that's the word I'm looking for. Amazon and other places allow that so that the number of servers can scale with the traffic. Then next year, at a million requests, you might need 100 servers, something like that. And you could add more for some overhead and things like that. But that's roughly the idea that I'm thinking about in terms of size. And then let me ask you a little bit about the size of the messages. So we talked about text. So would it be fair to say, hey, your typical message is about 100 bytes?
Yeah, that sounds accurate.
So at 10 billion messages sent per day and 100 bytes, so 10 billion is like 10 giga. So that would be 10 times 100 is 1,000 giga, which is a terabyte. So roughly a terabyte of data per day. And if you multiply that, per year, then now we're talking 365 terabytes. If you want to say a couple of years, 3 years, obviously that's roughly a petabyte of data. And so this also gives me a hint in terms of what kind of backend to maybe think about for this system design. So that's helpful. That gives me some ideas. And the other thing I want to ask you about non-functional requirements is what about availability, for example, of the system?
Yeah, sure. We want the system to be highly available. We don't want users to ever experience downtime.
Okay. Okay, makes sense. I mean, it's a live system. And then what about latency?
Yeah, typically we want things to happen in almost instantaneously, right? From a user perspective. So we're talking about hundreds of milliseconds for the API.
Okay. Okay. And so I'm going to make an assumption that we actually want hundreds of milliseconds or even just 100, whatever that number is in that range, that we want that for like the 90th or 95th percentile requests, meaning we don't want that for the 50th percentile, the average number of requests, because then we might have other 50% of requests that take way longer, and we don't want that. So we want the majority of the requests, the large majority of requests, to complete within a few hundred milliseconds. And so in terms of measuring these things, we want to make sure that we're monitoring, the average is good to monitor, but the 90th, 95th percentile, those their tail end latencies are more important to monitor. We want to have in place monitoring to be able to look at that so that we can make sure that we are actually hitting our targets there. So, 10 billion sent messages a day. We want, very low latency, and we want that to be available. So really, we want the system to feel very responsive and feel always available to users. That's kind of where I'm seeing this going.
Okay. Yeah, absolutely.
Okay. And then if I think about, I'm going to make an assumption here that because these messages, if I send you a message, it's not critical that I mean, we talked about latency in terms of response time to me as I'm sending it. And if you're on the receiving end and you're getting your messages, you want that to be responsive. But I don't make an assumption that it's not super important that when I send a message and I get a response back, that you immediately right then see the message. It's okay if it shows up, in just a second or two or three or something like that. So what I'm getting at there is, I think eventual consistency here is okay in terms of the data delivery. Is that fair?
Yeah, yeah, that's fair.
Okay. Okay, good. All right. I think those are kind of the most most important things I can think of at the moment in terms of functional, non-functional requirements.
With big system design questions like this, you want to quickly work out what's in and out of scope. Mark was able to do this fairly quickly, confirming the key functional and non-functional elements with the interviewer. You also want to reduce the scope. After all, you won't have time to design everything. Mark did this by excluding one aspect of the design, groups. It's generally a good idea to get to a working solution first, before scaling out and getting complex. If you try to cover all functionalities right from the off, you might never have time to actually get to a working solution. Before you start sketching out your high-level design, you'll also need to work out some key metrics and capacity planning to inform your decision making. However, you don't want to spend lots of time doing detailed calculations. Mark got the balance here just right. He did some quick maths to go from daily traffic to traffic per second, as well as coming up with a ballpark figure for the amounts of bytes needed.
So let's maybe do some quick API design. I think I've got a Google drawing here up that I'm going to use, and bear with me as this is not going to be pretty, but I'll try and do the best I can here. So what I'm just going to call this here Telegram mock. Let me just put talk a little bit about APIs, and then what I want to do is I want to get into the high level design, if that's okay.
Yeah, sounds good.
I'm going to try and if this text size doesn't work or whatever, just let me know. But I'm going to just talk about APIs right here. So I think of, in terms of the use cases we talked about, send a message, receive a message. I really think of 4 different APIs, maybe, or 3 or 4 APIs that I can think about. And I'm going to use very poor REST representation here, and I'm not going to do it for all of them. But so to start with, the REST API for sending a message might be, whatever the domain of this thing is going to be, telegram.co or something like that. And messages, maybe V1 for versioning. And let's see here. And then what I would do is the HTTP request, post request is probably the most appropriate thing with a body that contains sort of the information of this message. And so what would I want in this message? I guess I would want maybe the sender ID, which is identifying me as who's sending this thing. I probably would want, something like, it's either going to be some name mail thing that's sort of some identifier, or it's going to be some generated ID. I'm not sure. And then recipient ID, which is, who am I sending it to? And this could be, Jones, some number. And then maybe I would want the text, I guess, really, for purposes of what we're talking about. Pardon the capitalization here. That's just, hi there, how's it going? Something. And this would be roughly the body. And then I would get back as kind of standard HTTP response codes, 200 if everything is okay, 400 something if there's some sort of error, some limitations, maybe there's some other errors or something like that on the server side. So that would be roughly an API call to send the message to somebody. Just to be clear, the header of this message would have authentication to make sure I can't fake, the sender, etc., things like that. There'd be some standard things in here. So this would be one. So let me actually label this thing. This would be send a message. Okay. All right. So I said 4 APIs. So let me just run down the 4 APIs and we can kind of get. So there's check messages. And check messages would be basically seeing, do I have any new messages? And this, similarly to the other one, messages v1, and this might be a get request with there's no body, it's just a get request, and what it might return as a response is a list of messages, anyway, message IDs or something like that. So that would be to see, do I have any new messages if I'm on the receiving end of things. And then there might be like a read a message, and read a message might be similar to that. I'm not going to go into details here, but you get the idea that I would send a probably get request with a message ID actually. So it might be something like, yeah. So I wasn't going to go into detail here. I am. Message with the I'm going to just do this one briefly. Messages v1, and then I'm going to say message ID equals whatever the message ID is. So, and then there's a question. So here's a question about like, yeah. So I could mark messages as read. Message as read, for example, could be another API. Anyway, I should stop. Is that good enough for APIs? Does that kind of give you an idea of what? Okay, great.
Yeah, I think that gives
So let me
me
put that aside. I'm going to put that down in the corner if that's okay. I'm actually going to make that smaller now just to get it out of the way a little bit. So let me just think about this for a moment and see if I think about the so calculated some. I think we've covered functional and non-functional requirements. We've calculated some metrics that we need to pay attention to, and of course we want to look at total messages per day. As we're looking at growth and things like that. Um, in terms of high-level components, that might be a good thing to just sort of talk about a little bit, or kind of identify. So if I were to just draw some basic things here, I might say here's an application and slash user phone. And sorry, this is again it's a little smaller. And this application might talk to. We probably want, given the scale and given the requirements here, we will want a load balancer that winds up directing the traffic to a set of application servers that can scale, so that we distribute the load evenly. And there's different strategies to load balancing. You can wind up doing what's called round robin, where it just goes, it just kind of distributes one after the other one, just round robin as it's called. There could be one with least recently, least CPU or least loaded, I guess is the right term, where it looks at the load of the servers and it sends it to the ones that are least loaded. You can actually do the reverse too. There's reasons to do that, but we're not going to get into that. There's different load balancing strategies, but I think we need a load balancer here because we need to be able to scale. So, and then behind the load balancer, we would have basically app servers or API. Let me call them API server. And again, it's a little smaller so that this is a little bit. And then just to be super clear here, there's many of these. And I think we talked about when I was talking about the traffic numbers earlier. I think I said, maybe we want 50 of these roughly to handle, peak or something like that. So imagine there's 50 of these guys and the load balancer distributes that. Does that make sense?
Yeah, I don't think we did put a number in it, but I think that's right. 50 sounds about right.
Okay. To me. Yeah. So if we have, okay, so let me just recap that. So if we have 500,000 requests per second coming in for sends, this is only for sending. Each server, each API server, let's say can handle 10,000 send requests per second, then we would want 50 just doing the math. To be fair, getting messages might be more frequent actually than sending, especially in a group environment. We said we weren't going to talk about that, but so you might double that, right? So maybe we've got 100 or something like that. So that's the API servers. These are the things that basically take these APIs that we just talked about a moment ago and process the message, process the request, and translate that to what needs to happen in the backend server side. Is this visible? Okay. Is this? Is it? Are you able to see this? Okay. In the
yes.
Okay.
Yeah, that's good.
Let me just stop for just a moment, just to give you a chance if you have any questions or anything I'm missing so far.
No, looks good to me.
Okay. So let me continue with some of the components here that I'm thinking about. So if I jump, skip a couple of steps here, and me see if I can actually find one of these. Oh, look at that. There's actually a shape for, oh my gosh, a database. Database. So let's talk about the types of databases here. There's different types of databases that you could use for applications. There are mostly really two categories of databases. There are SQL databases, relational databases, maybe I should say, where you can do very complex queries. You can have complex data relationships, and that's a pro. That's a positive. And so it allows you very easily to query very complex, multifaceted types of data. The drawback of a database that is a SQL or relational database, of course, is that it's harder to scale those. And when I talked earlier about 100 bytes per message, 10 billion messages sent, we kind of extrapolated that out that at 3 years, you're at a petabyte of data. Now, 3 years later, maybe you're not really dealing with the old messages, but that's some detail. A petabyte of data, just to use that as a number or in that order of magnitude. The relational databases, that's hard to do because it's hard to have them all in one system and put a petabyte into one box and have a database that can handle the traffic of that. So what that means to me is that for purposes of this application, which we need to have scale and eventual consistency, we said is okay, then I would lean towards what's called a NoSQL database, which is, not SQL, meaning that you can't do these very complex relationships, or it's harder to do those, but they scale much better. And so I would probably go that route, and I would probably do something like, and I'm going to be even more specific here than NoSQL. I'm going to say like AWS, Amazon Web Services, DynamoDB is probably something I would choose.
Okay. Why would you choose DynamoDB? Obviously, there are other solutions available, Cassandra, for example. So why Dynamo?
Yeah, that's a fair question. You could absolutely use Cassandra, MongoDB, some of these other solutions. I would, I tend to I tend to think about engineers' time as very expensive, and so I would start with a hosted solution. So DynamoDB, Amazon Web Services, is a hosted solution where they manage the servers, and you're talking essentially to a cloud service. So I could actually, if I really wanted to be kind of a little bit silly here, I might, let me see here. Sorry, I might do something like this where it's basically a cloud. And so what that means is that Amazon is taking care of all of the servers and the uptime and et cetera, et cetera. And so we don't have to worry about that. And it turns out DynamoDB actually scales quite well. I mean, Amazon has got lots of customers using it. So it's a good solution. It may turn out actually that as we scale from a cost perspective, that we would want to run our own servers, and which you would need to do if we were using Cassandra or Mongo or so on. There's probably hosted solutions out there too, but from a cost perspective, it probably might be more effective for us to just have servers and run Cassandra instances in Mongo or MongoDB instances. So it's a fair question, and that might be a future thing to look at. But at the beginning, I would be thinking about getting this working and getting it working quickly with a reasonable, good solution that is a known solution. Does that make sense?
Yeah, that sounds fair. That makes sense. Thanks. Yeah, please continue.
Okay. So let me talk a little bit about. So one of the things I said I skipped a step here, and I did because here's these API servers, and here's this now cloud, I'm cloud DynamoDB database or whatever over here. How do you get to these things, right? And do you just talk to these, or how does that work? How does it know if there's multiple of these things? Really, it's because it's a cloud, it looks like one. So the scaling actually happens inside Amazon there, which is another nice benefit. We don't have to worry about it. But let's assume we had to worry about distributing this, or what's called partitioning, sharding this data across multiple servers or locations or instances or whatever, then these API servers that get a request would need to know where to go, where to send this traffic to. And let's see if I have this shape here somewhere. I think it might be something. Okay, let's try this and see whether this works. Okay, so I'm going to call this consistent hash smaller fits. So what a technology, a typical technology that's used often in distributed systems in order to partition this data space is what's called consistent hashing. And it's a way to take a large set of identifiers or space of data and break it down into buckets. And it's used all over the place. So it's nothing really new. And the reason it's called a hash ring is because you would have maybe draw here one more thing, servers, and I'm just gonna put here. This is a DB server isn't the right name here. That's not the right word. Backend. They call it backend server. That's a better name for it. You might at each one of these, and I think this might be 12 points or something, you might have 12 backend servers that are taking all of the traffic and are sending this to the database. And what this consistent hash ring basically does is it allows partitioning the space in a well-known way that can also scale if you add more user or IDs to the system. And so what I might do, and let me talk through this for a little bit more clearly, hopefully. So if I send a message, if I'm back down in this API and I want to send a message, and what this application is sending a message, there's a user ID, which is or the sender ID, which is it's me in this case for this particular example. The load balancer just picks an API server and passes that request on this API server here. And the API server now needs to know which database, which backend server do I send this to have it go to the database. And what it does is it looks at my name here, Clankmark 001345512, and there's probably a billion of these users. Maybe we didn't talk about number of users, but assume there's lots of users here. And it takes that number of users and boils them down into, in this case, maybe 12 buckets, assigns me based on my ID a bucket, and then that goes to a particular backend server. And so again, I'm hand waving a lot here, but you imagine that you have 12 of these little backend servers. And so I go to this backend server, the consistent hash ring would essentially assign me that. And that's done in the API server. So my request from a storage perspective, where does this get stored, goes to this backend server and then gets stored in the appropriate location. I am hand waving over a lot of this stuff, so I apologize. And we could go into depth here in more detail, but I kind of just want to mention the fact that this is a typical technology, consistent hashing, and I call it hash ring. Let me just get rid of that, make it easier. Consistent hashing is a well-known technology to do this kind of thing. And if I were using DynamoDB, I probably wouldn't have to worry about this because it's all built into Dynamo itself. So that's kind of the trick there. So this message would get sent all the way through and then it would get stored. So far so good.
Yeah, so far so good. Yeah, I'm with you. So good.
Great.
Mark's high-level design was clear and logical. He started with high-level components, identifying 4 APIs without going into too much detail, before moving on to outline the database. He talked well about the trade-offs between different types of databases and gave a good defense of his reasons for choosing Dynamo. When you make a decision like that, it's always good to share your thought process. Ideally, Mark would have shared his reasons without prompting.
Okay, so let me just take a look here. So I've started drawing this diagram a little bit. So what I want to do now is I want to make sure that I talk a little bit about the data here. And so I'm going to draw yet another box. Apologies, lots of boxes, lots of text boxes. That's just the way it goes. So what are the types of data that I need to be dealing with here in this Telegram, in this application, you know, for this particular purpose. And so I definitely need to have some sort of a table that has messages in it because I need to store messages. And so I would think that what I would need in this particular table is, let me just think about this. Probably want uh, like a sender ID, which is like the person who sent me sent the message. I probably want some sort of a message ID, which is the generated number. That's just a new, you know, it's just a new message. It's not something. It's a system internal kind of a thing. Let's see. What else do I? Oh, I probably want a timestamp because I want to know when the message got sent. And I probably want some sort of a status, like what's happened with this message. Is it been fully distributed to? Again, we weren't going to cover groups, but if we had groups, you know, has it been fully distributed to everyone in the group, or have they all seen it? Has it been in this case, in the case we discussed? Have you received my message? Basically, what's the status? Being super clean about my data types here, and then uh, I guess the other thing I would want in the message, maybe the recipient ID. Who am I sending this to? That's actually pretty important. And again, with groups, maybe that's a group ID. But so this would be I think what I would want to have for a table that has my that has my messages in it. So that's one set of data, and it turns out in Dynamo, one of the nice things about DynamoDB is that you can actually have a main key, which is really fast access, which could be, and which is actually turns out it's the partition key or the hash key, so works out nicely with this consistent hashing. Then you could have the message ID, which is just a number that just keeps increasing, and you can use that as I think it's called a range key, which is a secondary key. So there's some really nice fancy features in Dynamo that this data model for messages would work well for. So does that make sense?
Yeah, makes sense.
Okay, so let's talk about some other things that are important here. I think you also want to know about users, and I think for users, the important things for our purposes are you certainly have a user ID, which is like that would be my sender. If I'm sending a message, my user ID would be my sender ID, etc. Also uses my recipient ID, so that's important. There's also going to be a whole bunch of information like first name, last name, phone number, and things like that. I'm just not going to. I'm going to call this metadata because it's just like that's pretty obvious data. But what I think is important is I also need to know. I need to have for me as a user or for you as a user, I need to have what are the sent messages. Meaning, and these actually, let me be more clear. I think it would be sent message IDs. So what are the IDs of the messages that I've sent out to somebody? And then on the receiving side, let me think about this for a moment. I think I need to be able to distinguish between read messages, meaning ones that I've actually looked at and acknowledged and I've seen them, and unread messages. Because yeah, let me talk about that a little bit more for a moment, if that's okay.
Yeah, please do.
So if I look at the APIs here, right? So and we talked about latency. We want latency to be low. So if I'm wanting to have my messages be sort of updated reasonably timely, check message API. This is the backend API again. This is not necessarily on the phone, but it's in the backend. I want this to be able to return pretty quickly. And so how can this check messages return quickly? Well, one way to do it is by going, okay, so check messages goes through to an API server, and it goes to, and I'm gonna let me move these things here out of the way just a little bit and see if that actually works. Did that work? Hey, So let's assume that the hashing, this consistent hashing I talked about earlier, happens in Dynamo. So the API server gets a check messages request, and it goes to Dynamo. And what it can do, because of Dynamo's capability, and again, there's a feature there, and with Cassandra and Mongo, there's some, I think, some similar features to handcraft a little bit. But what I do is I might go and say, okay, for user ID Jones Tom 1389120, and I want to see what unread message IDs that person has. And that query can actually a column query in DynamoDB with a user ID as a key, user ID with a key left from your side, and the column query of unread messages. That's actually very quick in DynamoDB, and so that would return, near instantaneously. And so then what you could do is the check messages would be fast, getting the messages back. And then if you decide as a user, Tom Jones decides he wants to read a message, he could then invoke the read message API, and the read message API would go and fetch that actual message from the database. This table here, sender ID, message ID, timestamp. So that's a yeah, message ID. And then when you mark a message as read, and this is why I mentioned this in number 4, I think that marking message as read would move an unread message to the read messages column. So that way it wouldn't show up again. So that way you're explicitly marking messages as read, and when you check messages again after that message that you read wouldn't show up again. Does that make sense?
Yeah, okay, makes sense.
Okay, so we talked about messages, users. Similarly, like again with groups, we would have a separate table for groups and things like that. So that's kind of those are kind of the two tables. This is very crudely the system design. The thing that is missing here, I think, is I think there is a piece that's missing, which is when I send a message, the person that is to receive the message, Tom Jones in this case, Jones Tom, whatever, may not be online at the time. So I can't wait while I'm sending the message for Tom Jones to read the message. I just have to put it, my request to send the message just has to have it go into the database, messages with the information. And something else has to be able to realize that Tom Jones has a message. Now, one way to do that is when Tom Jones signs in on his application and it calls check messages, that they see they got this unread message IDs, that they get the message that I just sent in unread message IDs. But how does it get there is really the question. So I think we're missing a piece here. We're missing some sort of a, let me see, I'm just going to draw something here that is a, let's see, what is this thing? This might be some sort of a, I'm going to call it a message distributor, maybe. Maybe that's a good word for it. And by the way, I always tell people, don't worry so much about how things look, but here I am doing centering things and doing. Anyway, so the message distributor, I think it has to be some sort of a running job that's running independent of anything I'm doing or any other user is doing. And what this message distributor is doing is it's got to be looping over the message database and seeing the status of messages that have not yet been fully sent to anybody, and then take action. So let me see if I can be more specific here. Let me copy this. And here. Oops. I'm going to move the tables down just a bit here. And I'm going to change this and just make this into an example. So again, let's say sender ID here is message ID is some number, some big long number that's auto-generated. Timestamp is probably a 64-bit timestamp, which is like encoded. Do like this timestamp. And so now the interesting thing here, and recipient ID. Let's put recipient on here. Jones Tom. Now status is the reason that I wanted to do this example, because the status is the thing that determines whether the indicator has this message been sent. So I'm going to just say here, maybe this is called undelivered or something like that. Does that make sense?
Yeah, that sounds good.
So this message that I sent is undelivered. It's been sent, but it's undelivered. So this message distributed. So the messages is again, this is in a database, and this is basically there's a single row for every message with all of these bits of data in it. The message distributor, and now watch me do a watch this. This is going to be so artistic. Drawing an arrow. Sorry, call this a loop somehow. If you want, it's not a very good one, but it's close enough. So this message distributor is basically looping over all of the data, and it has to loop over all the data and make sure that it looks at all of the undelivered messages. And for each undelivered message, what it has to do is has to go, okay, who's this for? And so then it's got to look up that user and say, hey, in the separate table where there's the Tom Jones user, I'm going to add an unread message ID to Tom Jones's table, so that the next time Tom Jones checks his messages, that message ID shows up. Does that make sense?
Yeah, okay, yeah, that makes sense.
The hard part about this is that there's some lock and there's some hand waving big time over some issues of contention here that locking in contention that I'm going to hand wave over and we could go into, but I expect we may not have time. But in any case, this is the basic flow. So this message distributor, which just runs constantly, is going to go over all the messages and look for the undelivered messages to make sure that it can pick those up and then sign. Once it's put them into the unread message ID, in this case for Tom Jones or Jones Tom, at that point in time, then it will go back and need to change this to delivered, for example, right, to the status. And then next time it would skip over this. And for groups, again, like you can imagine that for groups, this gets more complicated because you have to make sure it gets delivered to everybody. So it might get more interesting, and the status might not be sufficient like that. But again, so I'm just noting that just for future. So now, one of the things that went through my head as I'm doing this is bottlenecks. So I think there's a bottleneck in this, the way I've designed the system, and that this message distributor, as we grow from, we said, we say a terabyte of data, new messages per day, to 360 to a petabyte over 3 years, right? So if you start with a billion messages, this message distributor might be okay. It'll go churn through all these messages. At some point in time, the data is going to grow so big that this thing might slow down. So this could be a bottleneck in terms of traversing all of these messages. So we're going to have to figure out a way, and I don't know off the top of my head. It might be that we need two separate tables. Actually, we might need a messages table that is a messages table for undelivered messages and delivered messages, or something like that. I'm not exactly sure. Or we need to make sure that Dynamo or whatever system we're using, Cassandra, Mongo, has a feature where we can do a filtered search that is very fast because it's low level at the database to skip over stuff that doesn't meet a certain criteria. Does that make sense?
Yeah, that makes sense.
So that's how I might solve that problem. But again, I'm doing a lot of hand waving. And this message distributor, by the way, I think this also has to scale. There have to be multiples of these message distributors partitioned across the data, because one probably can't handle it. So they need to be split across probably the user space, similarly to the API servers. I imagine it would be the same thing. That would, otherwise we would have another bottleneck, which is that this message distributor is just getting more and more traffic, and at some point in time it peters out, and one can't handle it. Never mind availability, but if we talked about availability.
Okay, well, I'm not gonna lie, I cannot focus right now. I think I'm gonna take a nap. And yeah, we'll keep on come back tomorrow and do more fun stuff. But yeah, I'm like kind of sleepy. Oh. Alrighty guys, see you tomorrow.